So let's start Danny's talk.
Okay. Thanks for organizing the event. It's my pleasure to speak here. So I'm going to talk about critical one-dimensional multi-particle DLA, which is a joint project with a fellow grad student, Dor Album, and my advisor, Alan Sly. So some of you may have heard about the model diffusion limited aggregation. So this is the model that describes a growth of a fractal. So on a domain, initially you have a single frozen particle at the center, and particles enter one by one, and one particle enters from infinity, performing a simple random walk until it touches the existing frozen component and freeze together. And after that, the next particle enters and repeats the same thing. So the top right picture is kind of a simulation in 2 dimensions, and the bottom right is what we can actually see in the nature. And mathematically, this is believed to be a very difficult problem in the sense that even the very basic question that one can ask is left open. So for instance, if xn is the diameter of the frozen component when n particles have entered, then we don't have a rigorous understanding on how xn should scale in n. So today's talk will be on a variant of this model, which is a multi-particle DLA. So previous model, the particles entered one by one, but now we assume that the particles are spread all across the domain under a certain density lambda, and they kind of perform independent continuous time simple random walk at all times until a particle attaches to the existing frozen component and then freeze together. So mathematically, a natural thing one can expect is that if the density of particles outside is very low, meaning that you have a fewer particles, then the aggregate will grow slower. On the other hand, if the density is high, then there are many more particles so that the aggregate will grow faster. And an interesting thing about the model is that it shows a different behavior when the dimension is equal to 1 versus the dimension is 2 or higher. So in the latter case, when the dimension is 2 or higher, it's conjectured that regardless of the density lambda, the diameter of the aggregate will always grow linear in time. And this is proved by Sidoravicius, Stauffer, and Sly under lambda that exceeds certain values. So like essentially for a large enough lambda. And when dimension is 1, it's expected to show a different behavior, and that will be the focus of today's talk. And I'll begin with introducing the model more formally. So we have an integer line. At the origin, there will be a single frozen particle in the beginning. On all other sites, we locate independent Poisson lambda number of particles at each site, where lambda is some fixed positive constant. And all particles will perform continuous time simple random walk independently, so they walk around. And when a particle right next to the frozen aggregate tries to jump left, then it will freeze and gets absorbed to the aggregate, and your frozen domain will grow by 1 step. And the random walk continues. And in this case, when a particle jumps to the aggregate, tries to jump to the aggregate, but then there are other particles at the same site, they will all going to freeze together at the same site. And again, the frozen frontier will grow just by 1. And even if your particle is right next to the aggregate, if it tries to jump right, then it will jump right and stay active. So our question is that if we call xt to be the length of the aggregate at time t, then how does xt scale in terms of t? And does the scaling differ in terms of the initial density lambda? So that will be our problem. So back in 2008, Kesten and Sidoravicius showed that when lambda is less than 1, then xt scales like square root of t. And the intuitive reason is the following. So if xt was L, then that means this aggregate has absorbed at least L particles. But since your density is less than 1, the Lth particle is located at position L over lambda, which is linear distance in L away from the aggregate. And a particle can travel square root of t distance until time t, so L should scale like square root of t. Okay, and then they also conjecture that in contrast, when lambda is greater than 1, it will grow like linearly. And if it's exactly equal to 1, then it should grow like t to the 2/3. And Alan a while ago showed the former case where he showed that xt over t when lambda is greater than 1 will converge to a constant almost surely when as t goes to infinity. And his proof was based on the infinitesimal speed of the process, which will be important in today's talk as well. So we will talk in more detail later. And also, Dembo and Tsai studied a variant of MDLA, which they call a frictionless model in the critical case, and they were able to establish t to the 2/3 scaling. By frictionless model, they kind of allow the aggregate to grow multiple steps at a time so that the length of the aggregate always equals to the total number of particles that have been absorbed so far. And that kind of flux condition guarantees some sort of nice monotonicity in the model. And by utilizing that, they were able to get to the t to the 2/3 scaling. So here is a simulation of this model. So in the subcritical case, we see kind of, I don't know, square root of t behavior and linear behavior in the supercritical case. So one thing we can see here is that the constant in front of the leading order appears to be deterministic. In contrast, when lambda is exactly equal to 1, the constant in front of the leading order also appears to be random, which will be clear from our result, which I'm going to introduce shortly. So before moving on to the result, I mentioned the infinitesimal speed of the model. So I'm going to clarify what that is first. So this is a plot of the aggregate in terms of time. So what governs the growth of the aggregate is that how many particles you have right next to the frontier. So if I define the speed to be 1/2 times the conditional expectation of the number of particles right next to the aggregate, where this 1/2 comes from the fact that each particle will jump to its left with rate 1/2, then all the story begins from the observation that xt is a Poisson process with rate st, although we won't have time to go into the actual proof of this. And which also means that, you know, the probability that x sub t plus dt is, you know, xt plus 1 with probability like st times dt. So basically this grows at rate s of t, and s of t will change depending on the history until time t. So to briefly discuss our result, we showed that if we rescale the length of the aggregate by t to the 2/3, then it converges to an integral of a diffusion given by this SDE. So it's pure, it has no drift, and it's like dRt equals 2 times RT to the 5/2 times dBt. To say a couple things about this SDE, we can see that RT is self-similar in the sense that if we rescale by t to the 1/3, we get the same law. Also, the frontier of the aggregate is given by the integral of this diffusion, and also this diffusion itself corresponds to the scaling limit of the speed. But the speed itself turns out to be something kind of chaotic, which is difficult to study, and this kind of scaling limit holds upon appropriate smoothing process. On the other hand, in the frictionless model studied by Dembo and Tsai, they also have an explicit description on the scale limit, but their scale limit turns out to have jumps, which is kind of a very different behavior from our scale limit, which is a differentiable curve. So for the remaining time, I'm going to say like a few words about the main ideas. So although we had this definition on the speed, this is still a complicated object because of this conditioning on the history. So the natural thing we attempt to do is we kind of plug in some other process that approximate our aggregate, which is easier to understand. And maybe the simplest candidate is by assuming that our aggregate has been growing at a fixed speed, which means that I'm going to just substitute x by some pi, which is a Poisson process with rate alpha. And an apparent advantage is that we can kind of explicitly compute stuffs. For instance, if we compute the expected value of the speed, it turns out to be lambda alpha minus some smaller order term. And what we can see from here is that if alpha is sufficiently small and if lambda is greater than 1, then the speed is going to be larger than alpha, which means that if the aggregate has dropped to a very slow speed for a while, then from then on, it will grow faster. So this gives kind of a mean reverting effect, which means that your slope cannot stay your speed cannot stay very slow for a long time. And this implies a linear growth. In contrast, when lambda is equal to 1, then we cannot gain anything from like comparing the leading orders. So now we really need to understand precisely the fluctuation of the actual speed from its expectation. And at the end, it turns out to be, so the speed turns out to be a perturbation of an age-dependent critical branching process. So by age-dependent, I mean that like each particle generates one additional particle in average, but then its children is generated at different location, which is given by some probability distribution. And by studying this critical branching process and other lower order terms that gives a perturbation, we can get down to the state scaling limit of the speed at the end. So I'm gonna finish my talk mentioning an open problem, which is also a future direction of work, which I think is interesting. So we were assuming that the initial distribution was IID Poisson of lambda, which is basically the stationary distribution under independent simple random walk. But we can ask what happens if we start with a different initial log. So we believe that it will still have the t to the 2/3 scaling, but then the limiting diffusion of the speed is different. So for instance, it's given by some minus 2/3 power of some Bessel process with this dimension. One interesting thing I want to mention here is that the Bessel process with dimension less than 2 is recurrent, meaning that our speed will be hitting infinity like infinitely often. So we kind of expect to see a non-differentiable scaling limit when the variance is above like 2. So yeah, I think that's a interesting kind of phenomenon to expect from this model. And yeah, thank you for listening, and I'm going to stop here.
Okay, thank you very much. Are there questions? I'm going to pause the